This is slide number 19 and I am your presenter Asloob Mudassar. This figure demonstrates that a plane wave front is incident on a biconvex lens, and the lens focuses the information at a plane which is known as the back focal plane, situated at a distance f equal to the focal length of the lens. Since the plane wave is incident, normally we have fx is equal to 0 and fy is equal to 0. The output at the back focal plane of the lens can be written as given below. Output is equal to double integrals of e to the power minus iota 2 pi, within bracket we have fx is equal to 0 multiplied by x and fy is equal to 0 multiplied by x, integrated over the dx and dy plane. And you know that here actually the plane wave is of infinite extent, the biconvex lens is of infinite extent, and the back focal plane size is of infinite extent, but we have shown them finite in extents. And on the lens we have shown the double integration, because the lens gathers all the energy from the plane wave and focuses at its back focal plane. So this is the expression that we can write for a normally incident plane waves on a lens. Now here we show different plane wave segments, each of infinite extent, but we have shown small segments of that one. So different plane waves are incident on the lens, and the lens focuses them at different points. And you see that at the back focal plane we have shown the black spots over there, which indicates the focusing of each plane wave segments corresponding to its unique focal point. And you know that since these plane waves are coming at different angles, we have shown the same integrals as shown previously, but here we have fx and fy. We have not specified the values of fx and fy. So for each segment you need to specify the value of fx and fy, and then the corresponding output on the left is given by output of fx and fy. So specify fx and fy for each input segment incident on the lens, and then each corresponding to each segment incident on the lens we have the unique output given by output of fx and fy in terms of this integral. And in this slide we now consider a unit amplitude normally incident plane wave. Again, you know that we know that when the plane wave is normal incident, we have fx is equal to 0, fy is equal to 0, so the overall plane wave is equal to 1. So this is actually the unit amplitude normal incident plane wave on an object O of x and y. Before that the plane waves were incident directly on the lens. Now we have in this case the plane wave which is normally incident not on the lens but on the object O of x and y. Diffracted wave front from O of xy can be decomposed into plane waves of different magnitudes going in different directions fx, fy, and incident on a biconvex lens. As we have shown in our previous case, we have indicated in the figure that different plane wave segments are incident. So in this case, when the unit amplitude plane wave will pass through the object O of xy, then due to diffraction at the object plane, different plane wave segments were generated after this object, and they were incident on the lens as we have shown in the previous diagram. And then now we can write the output in this case as O. We have indicated the output as capital O of fx and fy is equal to double integral of O of xy, which is in the space domain, multiplied by e to the power phase factor e to the power minus iota 2 pi into fx x plus fy integration with respect to x and y variables. Now you know that this is very important integral, and this integral is also referred to as the Fourier transform of the small object O of xy, and on the left hand side the capital O indicates the Fourier the contribution at the Fourier plane, and on the right hand side we have O of xy, which is the object at the space variables x and y. And this integral, you know that you should consider e to the power minus iota 2 pi fxx plus fyy, and the integration limits itself, they are actually you can consider as the part of the Fourier integrals, and this is the object that we need to put over in the integral in order to Fourier transform. So actually this integral gives you the Fourier transform of the small object O, which is defined in the space variables x and y, and we obtained the Fourier transform capital O with Fourier variables fx and fy, and here these fx and fy are the Fourier variables. So this integral gives you the definition of the Fourier transform. So we shall be using this integral repeatedly in the next few slides. And here now this is the end of slide number 19.